Next, I will explain the operation of BJT from the point view of the carrier movement, or what we call it carrier transport. So in this video, we will discuss on how the electron and hole move at the base emitter and collector junction. Okay, so first let's define or describe what do the emitter, base and collector mean. Okay, the first is emitter. So the word emitter refer to the process of emitting the carrier. Okay, for in case of NPN, so actually the emitter part emit the electron. Emit means produce, and it produce the electron and then force the electron to move to the next layer. So electron, so in emitter, the free electron will force to move towards the base, to the neighboring layer, or the layer beside. So we have here is emitter. If you see the structure here, this is emitter. The next layer is base. So the function of the emitter is to force the electron inside the emitter. Since this is emitter is n-type, many electron here. We have many electron here. So emitter will force the electron to move to p-type base. Okay, and then the base. What is the base? The base is where base is a thin layer. This is a thin layer. So in the base, the electron come from the emitter will pass through the base region. So ideally, we don't want to anything happen to this moving electron. So the moving electron should be proceed or passing through the base region and go and move towards the collector. Okay, and then here the last region is collector. Collector is the place where the moving electron is collected. Okay, that's why this is called collector. Okay, see the red color arrow is the movement of electron. So electron from emitter to base, and then from the base to the collector. Okay, so this is movement of electron. But in terms of the electrical current direction, the direction should be opposite of electron movement, because the current direction is defined by the positive particle movement, not a negative. Electron is negative particle movement, so it should be opposite of the electron movement. So the current direction of the collector, this is IC. The collector is from collector towards the emitter. Okay, so we have discussed the biasing condition and the type of operating region. Okay, so now we want to further discuss the movement of carrier. What really happened inside the NPN junction. So for the saturation region, this is where the base current is base emitter is fault bias. So fault bias, base emitter should be fault bias. You apply, this is a negative and this is a positive. And then here. So and then this one is collector base should be forward bias. So this is negative and this is a positive. So we have negative, positive, negative. Okay, so what happened? You see, if you analyze for every junction, base emitter junction and collector base junction, you find that base emitter junction is fault bias. So what will happen to the depletion region? So the depletion region here, so depletion decrease. Okay, depletion will decrease. And then when the depletion decrease, what happened? The electron can move from N-type to P-type. From N to P-type. Okay. Okay, and then the same goes to the collector base current. So this is electron movement. So what happened? The collector base also in fault bias. So the depletion region is very thin. So the depletion region is very thin. So this is depletion decrease. Depletion region decrease. So we have the electron movement from N-type to P-type. So N-type to P-type. Okay, so N-type to P-type. Okay, so what happened here is there will be a the increase of the current. Okay, increase of the current. Okay, so and then although this is the current at the emitter move to the base, and then the collector electron at the collector also move to a base, but the emitter, the current due to the movement of electron from the emitter is much more significant because of the higher doping of the emitter. So we can observe the rapid increase of current. Okay, and then another things that you can see is since both are fault bias, so fault bias in practical in ideal model, so fault bias can be replaced with short circuit. So means that the resistance of the junction is very small, so the resistance is low. Okay, so we have the both junction have very low resistance, so the total resistance across emitter toward collector is very low, so that's why we have the total low resistance. So if you plot the VCE versus IC, that's why you get the rapid increase of collector current. So this is saturation region. Okay, saturation region, although both junctions are fault biased, the collector terminal has insufficient voltage to collect all the free electron injected to the base. Okay. Okay. And the base current become larger than normal. This is because why the base current become larger than the normal? So the base current is actually this is the arrow that I wrote here is the movement of electron. So actually there will be more electron that will be contribute to the base because the electron come from emitter, and then another portion of electron come from the collector. So in total there will be more electron contributing to the base current. IC is maximum because the transistor is at its minimum resistance. So this is the one that I explained why we have the minimum resistance, because of both junction are in forward bias. So forward bias has very little amount of internal resistance. IC cannot increase any further even with a continued increase in IB. Okay, so this is saturation region. Okay, the last statement, if I want to comment, see you can, okay, you can see here, if you take the plot here, the current, so say if you put the current here, the voltage here, so this is a saturation region. So the saturation region, if you change or vary the IB, let's say 10 microampere to 20 or 30 microampere, the value will be not much change. It will be this at this value. Okay, this is what the last statement means. Okay, IC cannot increase any further even with a continued increase in base current. Okay, then the second operating region is cutoff region, where the base emitter is reverse bias. So reverse bias, positive at N type, negative at the P type. And then, okay, so this is collector. This is collector base. Collector base is reverse bias. So positive is at N type, and negative is at the P type. So what happened to the base emitter junction? The depletion region okay, what happened to the emitter base junction? The depletion region increased. So the depletion increase, and then electron inside the emitter cannot move. No electron, let's say, transport. Okay, so there's no electron from emitter to base. Okay, so for the collector base junction also, because since this is the collector base also for reverse bias, what happened is the depletion region also increase. Increase, and then same, no electron transport. Okay. In summary, what happened? Because there is no electron flow, so the current, total current IC is 0. And then because the depletion region both are reverse bias, so reverse bias of PN junction can be seen as an open circuit, so the resistance is almost infinity. So if you want to plot IC versus VCE, so you get a horizontal line at the bottom. So this is IC equal to 0. Okay, cutoff region is when both junctions are reverse biased, both depletion regions become wider. With large depletion layer, only an extreme small amount of reverse current pass from emitter to the collector. The collector cutoff current is small enough to ignore. Okay. And then lastly is active region. Active region is where the base emitter is forward bias. So this is negative, so this is positive, and then collector base in reverse bias. So reverse bias means that this is positive and this is negative. Okay. Okay. So what happened? Base emitter junction is forward bias, so the depletion region is very thin. So depletion region is very thin. Depletion is very thin. And then what happened to the electron in emitter? Can move to the p-type base. Okay. So, and then what happened to the collector base? But here collector base, this is reverse bias. The depletion region is higher or wider. The depletion region is wider. So there is no electron. So electron movement, no electron from collector to base. Okay, but however, okay, since emitter and base is fault bias, there will be many electron from emitter arriving at the base. So there will be many electron here. And then this is the collector is positively biased potential. This positive potential will pull the electron in the base towards the collector. So electron from emitter is pulled towards collector. Okay, so this, okay, although there is no the electron cannot move from right to the left, but electron can move from left to the right due to the applied voltage, positive applied voltage. So what happened? Current is not zero. So the collector current is not zero. So there will be a certain amount of current. And then how about the resistance? Okay, so this is the junction is connected in series. So you see the collector base is reverse bias. So open circuit, so resistance is quite high. So this should be high AC resistance. So the plot is, this is IC, this is VCE. The plot will be something like this. Okay, so we have the value of, let's say this 4 milliampere. We have certain value of collector current, but the AC resistance is infinity because this is a horizontal line. Horizontal line means that the slope is 0. When the slope is 0, the resistance is inverse of the slope, so the resistance is infinity. So in summary, if I plot again, this is IC versus VCE. Okay, the saturation region is where the current start to flow, okay, up again towards the maximum current, IC max. So this is a saturation region. At this saturation region, the R average is low, very low. Okay, and then at certain point, when VCE is higher, VCE is large, what happen? They will go to the active region mode. So active region mode is where the current is almost fixed at specific value. So here the current is not 0, but the resistance is infinity. So this is active region. Okay, and then the last one is in case of there is no current, the IC current is 0. This is I equal to 0, and the average resistance is almost infinity. This is what we call it cut-off region.